Alright, so in this video I'm gonna be explaining another important article with the title Differentiable Cluster Graph Neural Network. This paper in 2024 from National University of Singapore. So graph neural networks often struggle with long-range information propagation, and in the presence of heterophilous neighborhoods, we address both challenges with a unified framework that incorporates a clustering inductive bias into message passing mechanism using additional cluster nodes. Central to our approach is the formulation of an optimal transport-based implicit clustering objective function. However, the algorithm for solving the implicit objective function needs to be differentiable to enable end-to-end learning of GNN. To facilitate this, we adopt an entropy regularized objective function and propose an iterative optimization process alternating between solving for the cluster assignment and updating the node or cluster node embeddings. Notably, our derived closed-form optimization steps are themselves simple yet elegant message passing steps operating seamlessly on a bipartite graph of nodes and cluster nodes. Our clustering-based approach can effectively capture both local and global information, demonstrated by extensive experiments on both heterophilous and homophilous datasets. So on the left is an instance where distant nodes are similar to each other. On the right is the heterophilous ego network of node. Of node A, where cluster pattern appears. Square boxes indicate conceptual cluster centroid. So to embed the clustering inductive bias, we propose the use of differentiable clustering-based objective consisting of a weighted sum of global and local clustering terms. The global objective encourages clustering on all the nodes in the graph, while the local objective does on subsets of nodes, where each subset consists of a node in the graph and its immediate neighbors. Optimizing the objective function would produce a set of node embeddings that can then be used with a readout function for classifying the nodes of the graph. So we employ a block coordinate descent approach by iteratively solving for soft cluster assignment that probabilistically assigns a node to a cluster, followed by updating the node and cluster embeddings given the cluster assignment. So we view the first step of solving for assignment matrix as an optimal transport problem, which aims to find the most cost-effective way to move from one probability distribution to another. But for the second step, which is the updating the node and cluster embeddings, for the second step of updating node, we derive a closed-form solution that minimizes the objective function given the assignment matrix. The derived block coordinate descent can be viewed as a message passing algorithm on a bipartite graph with an additional set of cluster nodes. The cluster nodes represent cluster centroids, both globally of the entire graph and locally of each neighborhood. Importantly, our message passing steps act as optimization steps that enforce the clustering inductive bias. So we name it this differentiable cluster graph neural networks. So the methodology, we begin by constructing a bipartite graph. It is derived from original graph and comprises two distinct set of nodes. The first set is a direct copy of the nodes from the original graph. The second set consists of cluster nodes divided into two categories, global clusters and local clusters. So this is our bipartite graph. Each global cluster node connects to all nodes in V, thereby facilitating long-range interactions across distant nodes. So you can see that each node is connecting to its cluster. So it is a cluster node embedding, the C. And Z is just a node embedding that through a readout we use it for classification. So this minimization is just the optimal transport-based clustering objective function. So we propose our method to learn the node embedding. The transform features, together with the bipartite graph, are then put through an iterative process to produce the embedding of nodes and cluster nodes. A learnable readout function such as a simple MLP is then used on Z to produce the class probabilities in our node classification task. So we conceptualize the cluster assignment problem as an optimal transport problem, where the cost is defined as a distance between embedding of nodes and their cluster centroids. So these are cluster centroids, these are embedding of nodes. So we are comparing the distance between the nodes and their clusters. So this is global clustering, but they also have the local clustering. And another thing, node fidelity. So D represents the distance between the two vectors. Z is node embedding. X sub I node features after an initial transformation by a multi-layer perceptron. C sub j is just embedding of the j's, of course, global and local cluster nodes. Very complex clustering because they separated into global and local. The global clustering part optimizes the optimal transport between node embeddings and global cluster. The local clustering terms optimize the optimal transport between the embeddings of nodes and local cluster within each ego neighborhood. So since the convention of optimal transport solvers can be computationally prohibitive, we adopt the entropy regularized version of that. So it offers a good approximation of optimal transport. So let H be, this one is the entropy of the assignment matrix P. So we can have a refined objective function. Direct optimization of that as a training objective is intractable due to presence of unobserved assignment matrices, since we cannot compute this without estimating the cluster assignment values. So we propose an iterative block coordinate descent algorithm. So in each iteration, we alternatively optimize with respect to one block of variables at a time. Updating for assignment matrices. With node and cluster node embeddings kept constant, we aim to update them, minimizing the cluster loss. We approach this cluster assignment problem from the perspective of optimal transport theory. Assuming a uniform distribution of data points across all clusters, we aim to find a mapping from U to V, minimizing the overall cost. So this is the Frobenius dot product between P and M. And M can be seen as the cost of assigning node I to cluster J. This is the classical optimal transport problem. So this equation, this minimization problem, represents the optimal transport distance, also known as Earth mover's distance. While such problems are typically solved via linear programming techniques, these approaches are computationally expensive. To overcome it, we opt for the Sinkhorn distance, which offers a good approximation to the optimal transport distance with additional entropic regularization. So the benefit of having this entropic regularization term is that the solution now has a simple form, UBV. So this is the details of the Sinkhorn algorithm. So the big picture is this. We have embedding update. We update for cluster node embeddings. To minimize the cluster with respect to a specific cluster node, we differentiate cluster loss in terms of C sub j with other variables fixed and set the derivative to 0. If we choose the distance function d to be a square Euclidean norm, then the loss is a quadratic model of node embeddings. Then we can derive the following closed form solution. So similarly to cluster node embedding update, we derive the node embeddings update by differentiating the cluster loss with respect to Z sub I. And this is the appendix for broadcasted assignment matrices. That is just a mapping from index K of a node into ego neighborhood of node U to index I. So we can define the overall assignment matrix like these. And we can say P includes all the global and local cluster assignment matrices. You can see it in a single matrix. And then in appendix, they showed how to provide derivation of node embeddings, update function. So we calculate cluster assignment, node embeddings, and finally return the node embeddings. So our task is supervised node classification. We use cross-entropy loss. This one is essential, you know that. But along with two more regularization terms, these two, that there are orthogonality and similarity losses. For example, the orthogonality losses it encourages the clusters to be distinct, and we adopt a regularizing orthogonality loss function. And then the other one is sim. The similarity loss encourages node similarity to only a single cluster. So we set this number to be multiple of the number of classes and associate a set of cluster nodes within each class. And they use it for these, there are more homophilious rather than heterophilous graphs. Cora, CICER, PubMed. That's why nowadays we have 85-90% accuracy. But this paper is old, that's why they have low accuracy. Global clusters, for example, for Wisconsin dataset, you can see three neighbors match, accuracy in terms of depths of the tree.